Hi, everybody. Welcome to today's TurfNet University webinar, Managing Annual Bluegrass Weevil with Dr. Ben McGraw of Penn State University. We're doing our best here to keep everybody safe from coronavirus by doing our social distancing and handling all of our education online here. So you're in the safety of your office or home or wherever you're watching from today. So if you have any questions for Dr. McGraw, you can go ahead and pop those into your um, question and answer box there. And as soon as he shows his screen, we'll get going. And I just want to give a quick shout out to our corporate partners here, um, BASF and Greg, as well as Brandt. And so thanks to them for bringing this to you. They've been part of this for a long time, and we couldn't do any of this without their help. So thanks to all those guys. And so once again, if you have any questions, just go ahead and put those in. And we hope that everybody enjoys today's presentation. Ben, you can take it away whenever you're ready.
Great, thanks, John. Hopefully you can give me the thumbs up that you can see my screen and hear me all right.
Looks and sounds good.
Awesome. Well, I probably shouldn't do this, but I always look to see who's on this webinar. And man, there's some heavy hitters on here who could probably do an equally fine job of presenting this material here. So hopefully I don't disappoint. Hopefully everyone's nice and healthy and staying safe out there. But John asked me to provide kind of an update on what's going on in the annual bluegrass weevil world and what we expect to see in 2020. There's some changes coming up, some changes coming down the pipeline, I do believe. Some new products, potentially some existing products that might go offline, and also kind of showcase some of the things that we're doing here at Penn State. But lately, I've been thinking, a lot about kind of the history of this insect and some real challenges with this insect. Recently, I read a paper from 2015 on Colorado potato beetle, which is very similar to the annual bluegrass weevil in the sense it's in its ability to develop resistance to insecticides. And then in the paper, the authors talked about the red queen effect, which is an effect that is related in the evolutionary biology world. If you remember from Through the Looking Glass, Lewis Carroll's book, Alice in Wonderland, that Alice and the Queen were running at a very high pace, and when they stopped, they noticed that they were basically in the same situations. And the red queen effect in the evolutionary biology is this phenomenon where insects must constantly adapt just to simply survive, just to persist, to keep up with their competition. And we do see that as a co-evolutionary arms race, basically between insects and plants. So plants develop toxins over time, over long periods of time, to resist the insects that feed on them. Insects have evolved means around that. It goes back and forth, back and forth. And lately, I've been thinking about that with this insect, mostly in the pressures that we put on the insect when we spray insecticides. So if you think about the history of turf grass, is very short in evolutionary biology terms. Insects that feed on turf grass is even shorter. And then really the advent of chemical insecticides, even shorter, yet we're really kind of ramping up this pace that we're chasing after this insect. And this insect is evolving means around those pressures that we put on them. I think this is the tweet of 2019. I don't know Keith Kruger, but hopefully get to meet him one day, because I think this really summed up the pace that we're running in place with the annual bluegrass weevil, where Keith said 7 ABW applications by July 4th and still seeing damage. Maybe it's time to change your program. And I think that really summed up our year in 2019 and really summed up the couple of years that we've had with this insect. So things are becoming more and more challenging. Some of these things are self-inflicted. I hate to have to say that, but it is largely true that we put ourselves in these positions where it's a constant assault against this insect over time. So, I returned to this publication, this very, very early work, one of the earliest works that I'm aware of with annual bluegrass weevil work, to kind of gauge where we are 50 years later at managing against this pest. So Scott Cameron and Norman Johnson were scientists at Cornell, And they were really the first people to study this insect on Long Island, including looking at some of the early insecticides and doing some of the early chemical trial works to really see how we get to this position. So at that time, the insect was classified in the Hyperotes genus, and really within their paper, they put out there that we really don't know how long we've been dealing with this insect in turf grass. And that is interesting to note, and I guess I had forgotten this from the time that I would have been reading this during my PhD, that some of this early damage is on grass tennis courts on the Long Island area, but potentially this insect could have been damaging turf grass as far back as the 1930s, or as they posit, as far back as to when golf courses were, first being established in this country. So we really don't know exactly when this insect was damaging turf grass, but we have a pretty good idea that it's been damaging it since the 30s, but definitely for the last 50 years. These authors also, shortly after that kind of publication came out, they also published some of the early chemical control work. So you imagine right after World War II, when a lot of the chemical insecticides between the 1940s and 1970s really came on the market, there were lots of broad spectrum contact insecticides. And this was a new insect, and these scientists did what scientists do and kind of put the battery of insecticides against the insect, and really kind of developed this chart with the known toxicity against the insect in the adult stage. And you look at some of these chemicals that they used way back when, and you can see that these are some really persistent broad spectrum insecticides. If you look at number 17 on the list, DDT was not even one of the most effective ones against this insect. Out of these 25, some of them might pop up, like diazinon might be familiar to some of you. Chlordane was a very popular white grub, very persistent white grub insecticide, not being overly effective against the weevil. Malathion, number 7 on the list, also a very common insecticide as well. Of all of these products or active ingredients, you can still see Dursban up there at number 4, which we still have as far as spring of 2020 in our arsenal. So really huge battery of tests. It's interesting to note that these early chemical control trials were conducted on grass tennis courts on Long Island. Pretty interesting sampling technique that they have with the series of rings to rate quality damage. But what the authors concluded from these chemical trials are some philosophies that we still hold to this day, in that they suggest that it's all about timing, that the annual bluegrass weevil can be controlled when insecticides are applied at the proper times. And I do think that this is, this isn't anything earth-shattering to those of you on the line here. But what we see is, even at this early time, 50 years ago, when these trials were conducted, that this traditional management, this idea of applying controls against the adults, emerges. And they would suggest that control is best achieved when you apply it either in late April or early May in Long Island, or to be sure, at both times, which is something that we don't promote to this day. As we moved into the late 1970s, early 1980s, I think we started to really kind of finesse our understanding of how the insect behaves in the environment. Pat Vittum's work with her major professor, Tashiro, at Cornell, really looked at the biology and the ecology of the insect, and we gained a much greater perspective about how these little buggers were moving throughout the environment. So I would contend, really, in the 1980s, there was a pretty good lull, at least in the research, what's mentioned in the literature of being a problem, until about the 1990s. And at the 1990s, that's when we really start to see anthracnose being more of a widespread issue. We also see the weevil becoming more of an issue. And I think one thing that we tend to overlook is really the differences in that time period. If we look at the 1970s, this was probably a typical fairway, whereas by the 1990s, all of a sudden we're mowing much lower. Our nitrogen inputs are probably decreasing quite a bit. At least we know that from the anthracnose side of things. So there's some major changes that are going on in the management of golf courses, which ultimately affects the host that the insect is feeding on. So it could have been a really bad period of time, I think, just by adapting the host to something that is more likely to express damage. However, we also saw that this was the period when the pyrethroids really came onto the market. So in place of that long list of really broad spectrum insecticides that are, most, if not all of them, with the exception of Dursban, have been phased out, we see that the pyrethroids offered a much more effective control of the adult stage. So we haven't really done anything to go after the larval stages of the insect by the 1990s, but really at this time, one application or a couple applications, as the early studies suggested, were sufficient to control populations for the rest of the year. So the pyrethroids had a biological or a botanical base, if you will. The pyrethrum derived from chrysanthemum flowers. The pyrethroids were a synthetic version of that active ingredient. So traditional management was still in place, where we're trying to control the insect as it migrates in from overwintering sites. So this could be in a tree line, such as on the left side, or tall grasses, such as the right side, or oftentimes we'll have populations kind of converge from two different areas. So the idea here was we wait until they're out on the short mowed turf and we hit them with these insecticides. Now, there are some problems with this theory, and one is that they're very mobile stage. Often we can see a couple of waves of immigration coming in, and that's most likely due to taking a normal distribution of insects, but also subjecting them to changes in weather. So insects are cold-blooded. They're going to be only as active as the temperature allows. If we have warm days, the tip of the iceberg migrates in, and we have followed by cold days, they might be in suspended animation. The other problem too is if we treat too early, even the pyrethroids did not greatly increase the residual activity of the earlier products. So you apply them, and within several days, that compound is broken down. However, the traditional management is still a very popular means and can be a very effective control strategy even today. As we advanced into the 2000s, this is really where we're kind of running in place again with the Red Queen, if you will. So pyrethroid resistance was documented for the first time in southern New England. Our colleagues at University of Rhode Island, the University of Connecticut, and Massachusetts began to notice a decrease in the sensitivity of many populations where pyrethroids had been used extensively, not only in space, wall-to-wall applications, but in time, where it was not uncommon in the early 2000s to meet superintendents who would mention that they would put a pyrethroid in the tank every 2 weeks just to clean up whatever was out there. They were inexpensive, and so it wasn't a big draw on the budget. However, what I find to be even scarier, and again, we're running at an Olympic pace with the Red Queen here, is multiple resistance, or the understanding that when we select for high levels of pyrethroid resistance, we may be selecting for resistance to unrelated compounds, so non-pyrethroid compounds. This may be towards another adulticide, such as Dursban or chlorpyrifos, or it could be towards a larvicide, such as chlorantraniliprole or acelepryn. So very scary situation. I would say the one plus during the 2000s is that we saw a great discovery from our industry partners. A lot of new products coming online. The anthranilic diamides being one of the greatest, I think, achievements in insecticide discovery in at least the last 50 years. Other things like intoxicard, Provant, which is another very effective product. And, you had more people looking at some of these problems. So all kind of positive. So trying to keep up with the insect by running in place with it, if you will. As we advance into the last decade, we really see this insect, again, adapting as it moves throughout the region, being able to feed on hosts that we didn't think it was possible for them to develop on, such as creeping bentgrass. There are some reports of damage to perennial ryegrass also as the insect moves into the mid-Atlantic or even more southern populations. And we're also seeing lots of movement of this insect in things like sod. So recently, introductions into Arkansas as well as Kentucky. I can speak to the Kentucky population that it does seem to have established very well. And I have not kept up on whether or not the Arkansas population has established after it was introduced in sod. But this is a growing concern for many of us who study this insect. One thing that I typically do not see a whole lot of, but is also indicative of this insect being able to adapt and kind of stay one step ahead of us, is damage to the roughs. So last year in Pittsburgh, we often would find damage to high heights of cut. This is turf that's mowed at about 2 inches, and weevil larvae doing just fine in these areas. I would suggest that earlier in the spring, when we're coming out of winter and the insects are migrating through these areas, this is very compact boa. So even though it's mowed at a rough height, it is much lower than what it has grown at by the end of May when we started to see the damage. However, we also see the insect in these areas, such as the western extent, into Ohio, western Pennsylvania. We do see that we have more generations per year. It appears damage occurring much, much later in the year. So typically we used to only witness extreme damage in the end of May, early June, in most places throughout the distribution. Now we're starting to see damage well into September in these kind of extreme areas. And then another one, which our turf grass managers who manage athletic fields think is a great thing, although this turf grass manager didn't think it was a great thing, is we're starting to see damage to athletic surfaces. So this is in close proximity to some known annual bluegrass weevil damage on golf course height turf grass. They must have migrated their way across the street and began chewing on these isolated patches of annual bluegrass in amongst Kentucky bluegrass, perennial ryegrass mixes. So this is an undisclosed location in central Pennsylvania at a major university across from a turfgrass research facility. This was about a week before the women's soccer team showed up at this undisclosed location in central Pennsylvania. And the coach was not too happy with this practice field, but this was the first instance that I've seen damage to about 1.25 inches height turf. So there are some pressing issues moving forward in 2020. It is a difficult time in regulatory environment, just climate-wise. But these are some of the biggest issues that I see facing us as managers of the weevil. One is really a lack of control options for that traditional timing. When we time them against the adult, we know that this can be a very effective strategy if you control the adult insect to avoid egg laying, or to at least compress the egg laying window and to allow our larvicides to work that much better. We also hardly ever find a weevil population in areas where we have damage that has really early 2000s levels of sensitivity to the pyrethroids. So insecticide resistance, as well as multiple resistance, is a huge, huge concern, not only for the products that we have now, but products that we will develop in the future. And as I alluded to, I do believe that we will start to see some products leave the marketplace. Hopefully, the creation of new active ingredients can keep up with this, but it is very expensive and involves a ton of research and data to bring a new product to market. So I do think that what we will see is the loss of products kind of exceeding the creation of new active ingredients. But a big one, whether we have a bountiful number of products or not, is we do have some real environmental challenges. The 2018, 2019 were some of the wettest on record. So out of the 124 years in this period of 1895 to 2019, or 125, you can see that it was the second wettest during the period of July 2018 to 2019 in much of the area where the weevil is most problematic. So this really challenges kind of the longevity of our products that we put out in the environment. It challenges just really the overall operation of managing turf as well. So these are some extreme challenges. Where it's hot and dry, where we have extreme droughty summers, we just see damage really being exacerbated by even low population densities of weevils. So, what is the path forward? Hopefully, we can not be all doom and gloom in this webinar, but really the path forward has to involve cultural practices, really understanding about what our cultural practices, what impacts they have on weevil densities, keeping them below thresholds, or even removing them from certain areas. But I do think that, we will be looking towards the next generation of scientists, in particular our graduate students who do a majority of the work, to come up with solutions such as plant defenses, or even monitoring technologies that allow us to detect populations that are in damaging levels ahead of damage expression. And really, I think we're looking towards the soil as well as within insect guts to come up with novel ways of using these microbes against the insect itself. So it's not all doom and gloom, but we do need a lot of work to really catch up with this insect so that we're at least surviving, or at least running in place to keep up. So largely what I'm going to talk about today is chemical management of this insect. So those are some of the more pressing and kind of changing environments that we see with this insect, as well as some of our projects that we have to make our chemicals work that much better. But really, the best foot forward as far as managing this insect right now still involves chemical management. I just think we need to be much more deliberate and conscious of how we're applying products, limiting the total that we put out there in the environment, not just an area wall to wall, limiting the space and not doing wall to wall applications, but also really tightening up those applications across the season. It really does seem counterintuitive, but the more that you can not spray is sometimes often the best management strategy. So really tightening up these applications and being very deliberate means starting off on a good foot. It is my firm belief, and it might not be a popular belief, but it is my belief that we must control the adult generation, the overwintering generation that's emerging, to really set us in the right path for the rest of the year by condensing the amount of eggs that are placed throughout the season, by allowing a smaller population to be treated by larvicides. I think is the best way to get off on that good foot. Really being intentional with our timing, having it being based on really ground truthing, really well thought out things, thinking about what you've used in the past, rotating active ingredients. Those are all really, really sound IPM approaches. The other thing too is I would not expect 100% control. So as we've moved into the 2020s, if you looked at some of our single application trial data, where we might get 50 or 60% control with a single product being applied against the spring generation, I'm telling you right now, that's really good. I think we've been long conditioned into expecting to see products perform at a 90% or above control, and that may be doable in small plot trials. But in a realistic manner, what we're trying to do is just avoid turf grass loss. And sometimes with this insect, 50 to 60% control with a single application is dynamite. So what's susceptible? I like showing this photo because it kind of shows all the stages that the insect has, and it kind of illustrates really the susceptibility of the insect as well. So we have the first three larval instars are stem borers. The female is going to chew a hole in the plant where she places her eggs. Those eggs will hatch out and then become these stem borers. The red arrow indicates really the stages that we're most concerned about. The fourth and fifth instars are crown feeders. So they're going to feed externally. They're going to be too large to fit inside the stem of the plant. Therefore, they're going to feed externally on the crown. They are actually susceptible to some of our chemical insecticides. Our in-plant stages, our stem borers, are really going to be largely protected from a lot of things that may not have translaminar activity, may be true contacts, as well as our pupae. So our pupal stages, as the time that it moves between the late larval instar and this callow or teneral adult in orange, it's going to be largely protected. So when a lot of the population is in the pupa stage, it might be just best to wait out and see what happens. It's a dormant non-feeding stage, so there's not much concern. So apart from the crown feeders that we have to be really on our toes about detecting, the only other stage that's really truly susceptible is the adult stage. And again, I've already mentioned the issues with targeting the adults. They're mobile. They can burrow in and out of the thatch. Our products are really kind of don't have great residual activity, so there's lots of issues there. But the overwintering population really represents a time of the year where there's only one stage present. After egg laying and egg hatch occur, then we're going to have more than one stage around. So really two opportunities for control. So what we will see is some of our products do have residual activity, and they might be placed down when the insects are inside the plant, or possibly those products have some translaminar activity that might control the insect within the stem of the plant. Sometimes we place those at that timing so that they're able to acquire that toxin when they emerge from the plant. So what's available within the US for adulticides? It's fairly limited. We have 3 to 4 pyrethroids that are available, and we have 2 organophosphates, chlorpyrifos and acephate. These are all contacts in the truest sense of the word, that they're going to control whatever they come in contact with. They're not going to persist very long in the environment. It's not going to be very selective. It's not going to discriminate against different insects. And they all are bound quite tightly to organic matter. So really, if you think about that, getting in contact with the insect is going to be very important. The other thing that you notice from these two lists, we have 2 classes with 5 active ingredients. It doesn't allow itself for great buffet or selectivity of products. There are also some combination products, things that combine either a pyrethroid or an organophosphate in the case of Avatar with something like a neonicotinoid. So Triple Crown has 3 active ingredients, 2 pyrethroids, and midocloprid, which is a neonicotinoid. So those products, in my opinion, really are best used against the adult stage. I know that some people use them later on as larvicides. I do believe from our limited data set that the primary action is controlling the adult stage so that fewer eggs are laid later on. If we have anybody from Canada on the line, given several talks in Canada recently, and really their buffet is much smaller than ours. So again, 2 classes, but only 2 active ingredients. And what we can see is they don't have any of the combination products. However, they do have clothianidin, so essentially making their own aloft. So the attributes are the same. The active ingredients are much less. And the main concern that we have in a situation like this is pyrethroids, we know have issues with resistance development in this insect. And then the other one is chlorpyrifos. So I know that New York State is slated to remove chlorpyrifos. If this insect were a problem in California, I believe California is also going to be banning chlorpyrifos pretty soon. And I think the real issue is I'm not sure that the companies producing chlorpyrifos are going to have much desire to make this product in the future. So I really see 2020 as being the last year that many places will have chlorpyrifos, whether out of government restriction or statewide restrictions, or whether it's a manufacturing issue. But that is my main concern. This product has had a great lifespan, at least 50 years, if not more, 60 years. However, it does have some inherent issues. That does not take away from the fact that it is a very important tool in ABW management. So why am I touting adulticides at all when we do have some issues, whether with mammalian toxicity of chlorpyrifos or with resistance development in the pyrethroids? And it's this. I think it's incredibly important to kind of maintain somewhat of a consistent population as it develops through spring. So this was from one of our chemical trials that we conducted in 2019 in May, and this was mid-May. And already by mid-May, if we took a plug from this area that's starting to show a little bit of chlorosis, we take a cup cutter out of here and we separate out all the larvae. You can see on the filter paper on the right-hand side, we have every stage from first instar through fourth instar. And this is a phenomenon that we see throughout the year as we advance past the first generation. In the first generation, we have adults appearing all at once, and hopefully if we control them, you're not going to get 100% control, but it's going to tighten up the variability or the range of stages that we have. And so that allows us to use larvicides much more effectively. If I have insects that are still in the plant and insects that are emerging from the plant, that's asking an awful lot of our product to stick around where it's going to control many of those. And really, we don't have too many products that provide extended residual activity where it could be placed down when they're still at a first instar to get them when they emerge from the plant. So another thing that we have to consider is if we don't control the adults at all, the female has an amazing ability to lay eggs over a very long period of time. So this is a study that I conducted in 2012 and 13, where we tracked individual female egg laying over time. So we placed them in containers where they could not be picked off by birds or hit by mowers. And we placed them on annual bluegrass for 7 days. We would remove them and move them to new POA plugs, and we would peel back the tillers from the other plugs and count the number of eggs. And what you see is it's kind of erratic in the first 8 weeks of egg laying because the temperature is going up and down. So again, insects are cold-blooded. Egg laying is kind of very tightly correlated with temperature. And what we see is that, you know, even though she deposits most of her eggs over this 8-week period, we can see that there is a small production for another 7 weeks after that. So upwards of 14, 15 weeks, the female can place these eggs. At her maximum, she's producing on average about 3 eggs per day. So about 90 eggs over the period of time. So if we even take the bulk of the egg laying, that 8-week period, that's 2 months that an insect that could be coming out potentially, I mean, we're rolling about 3.5 weeks early this season. We could potentially have insects on the move within the next couple of weeks, laying eggs all the way up until June. And so that leads to that overlapping generations much earlier in the year than we typically expect. That's what we expect with the second and third generations. So some people have asked, you know, if we're going to treat the adults, why don't we treat the adults early and why don't we treat them often? And this was really kind of the recommendations that were being made about a decade ago, where some people were going out on the recommendations of some people to apply a neonicotinoid along with the pyrethroid, so that could be your combination product. And they were told to apply them to the roughs as well as the short turf areas, pretty much wall to wall, very early in spring before forsythia was even blooming, and then repeat that 20 days later with a backup application. And the theory there was that the insect is going to come out of overwintering, it's going to feed on the turf that's been treated, and it's going to die immediately rather than even getting to the short turf areas. So it was mostly treating the roughs, which is a very difficult thing to control an insect that's moving through a 2 to 2.5 inch rough. So eliminate egg laying, you know, before they even get to the short turf. That's a great theory, but it's really on the basis of, it hinges on the basis of whether or not that insect feeds on the way in. So you might be wondering why I have a male testes and a female reproductive tract on the bottom. What we did over a 3-year period from 2011 to 13 is we dissected insects that emerged from overwintering and had just arrived on the fairways to see whether or not, one, they had any food in their gut, but two, if they were reproductively mature and had the ability to lay eggs. So the female, if you see the female on the bottom here, the E points to the egg, she can produce an egg if it's not fertilized, it's not going to become a larva. So it's basically like a missile without a warhead. And what we saw was that females actually showed up on fairways pretty much ready to go, reproductively mature, well-developed reproductive systems, but the males did not. They lagged behind. They had really immature reproductive systems, so they could mate with them, and we'd often find them mating with females in the act of mating, but they didn't have any, as it was put to me, lead in their pencils. So they did not have the ability to inseminate the female or fertilize that egg. So very few females were mated prior to winter. So, and this has been seen in other studies, less than 20% of females are going to have sperm in their spermatheca that could fertilize an egg. So really they didn't represent much of a threat as far as egg laying, but as far as acquiring the toxin, very few of them had fresh food in their gut. So the insect walks out in springtime, largely breaking down their muscles, reabsorbing those muscles so that they can derive energy from that, so that they walk in. That's why they don't fly in. And they really don't seem to feed much until they've dropped most of their eggs. So pretty shocking findings, but it really kind of eliminates that idea of applying an adulticide to the rough in advance of them getting to the short turf. It's much better to wait until they're all out of overwintering sites and then apply those compounds. Another thing that we have recently looked at is really simple study that we probably should have done a really long time ago, is just kind of determining how long do these adulticides last. So I always ask, when I was asked how long a pyrethroid would last, I would always say, geez, I don't know, but I would assume it would be about 7 to 10 days and then it would wear off. So what we did is, if I can just back up, maybe I can back up. There we go. We had these plots that we treated with insects over the top of them. And then we had some plots that we would treat on day one, and we'd cage the adult a day later, 3 days later, or 7 days later to get the idea of residual activity. Then we'd come back and assess mortality after 48 hours. So this is a moderately resistant ABW population. So you would expect that the pyrethroid, so bifenthrin here in the light or moderately green bar, I guess, pretty poor color choices for my graph, but the third bar over is your pyrethroid, is giving us about 30% control. That's what I would expect in a moderately resistant population if we spray over the top. Chlorpyrifos was about 50% control. If we look at what happens on the insects that we put on the turf 1 day after spraying, you can see the control of all these adulticides goes down dramatically. Again, 3 days later, and by 7 days, it's pretty much non-existent. So I would say from these limited data, these data would suggest that you really need to have the most impact on an adult population with an adulticide is you need to have it sprayed over the top of the insect. If the insect walks into treated turf a day or 3 days or 7 days later, that impact is going to be severely, severely diminished. So in a study that we conducted, a former master's student and I conducted, where we wanted to understand when the insect was on top of the canopy to possibly be removed by mowing, I think this has implications for our adulticide applications as well. We assumed at the time that the insect was rather nocturnal, like most weevils become really active right around dusk. And so what we did is we wanted to track their movement throughout the night, but as well as the day. We containerized these weevils in these plots, and we marked them with a fluorescent dye and then photographed them every couple hours or every hour on the hour for 24 hours. And the camera was fit with a filter so that you could see them fluoresce when they were on top. If they were burrowed down in the canopy, we could not see them. And what we actually saw is not surprising, and it's something that we should have hypothesized from the beginning, but that's why we do these studies, is the insect's activity on top of the canopy was tightly correlated with temperature. So in the early months of the season, such as now, March, April, the insect is really most active as the day goes on. So at the, almost at the highest temperature points of the day, because we're not getting much above 65 at this time of the year, the insect is most active in line with temperature. Same thing in May, But what we saw in June is that as temperatures get above 20 degrees Celsius, so above 70, 72-ish, the insect would burrow back down into the ground. So at low temperatures, the insect is going to be hunkered down in the turf. And at high temperatures, it's probably trying to avoid the heat. So it's kind of this bell-shaped curve as far as surface activity. So what our model would suggest is between 57 and 64 degrees Fahrenheit is when the insect's going to be most active on the surface. And we probably have all seen this, where you're walking greens on a warm spring day, probably where the temperatures are in this range, you can see adults fairly active on the surface. So there was a little bit of surface activity above and below this, but this is when maximum surface activity would occur. And when we likely hypothesize that, or we do hypothesize that adulticides would have their greatest effect because of that direct contact with the insect. We are looking into alternative adulticides, fearing that this is coming down the line, that these products are going to be removed. Over the last few years, we have looked at things like oils, like Civitas, that many are familiar with, mostly used in disease management, as well as wetting agents. Various surfactants have known to have insecticidal properties. And how these products work is really by breaking down surface tension on the outside of the insect. We thought that it would clog up the breathing apparatus, the spiracles on the side of the insect, and kind of cause it to suffocate. But when we performed dissections of the insect, we could see, at least with Civitas in the dye, that this was breaking down surface tension, allowing the product to move inside the insect and most likely flooding the insect from inside. So to you, it probably doesn't matter how they die. This was a pretty exciting discovery because it provided very rapid death. Mortality was mostly observed within 3 hours in laboratory and greenhouse trials, very high levels of activity with very low amounts. When we went to the field, we did know that water was going to be a key factor in controlling insects with Civitas or surfactants. I'm just going to show the Civitas data. Basically, how we ramped up the different moisture in the environment was pre-irrigating to saturation. So our TDR readings were reading between 45 and 47% volumetric water content. We were going with a half rate of Civitas. And basically, we apply it over the top and either water it in or provide a high carrier volume, either 1, 2, or 4 gallons per thousand, or we come back and we irrigate with either no post-application irrigation, 1/10 of an inch or 2/10 of an inch. So we suspected, based on what we had seen in the lab in the greenhouse, that more water was better. We're already starting with a saturated base, and we would expect that a higher carrier volume or a higher post-application irrigation volume would work best. And what we saw was the opposite for both carrier volume and post-application irrigation. The control of the adults, basically we come by, and as my technician Danny Klein is doing here on his hands and knees, we apply a soap to extract all the live adults out of the turf. And what we saw was about 50% control of adults when the lowest carrier volume was used. As far as larvae, I would take these data with a grain of salt, only because after we control them, these products break down immediately. There's no residual activity. New adults can come in and lay eggs in these treatments. But really, it wasn't a huge reduction in larvae, but I'm most concerned in the control of the adults. So 50% with 1 gallon per thousand carrier. We also saw about 50% control without any post-application irrigation. So it may be in this case that we had too much water in the system. It was saturated soils. It's possible that that product was too diluted or not enough came in contact with the insect with the excess amount of moisture. So there's a lot to really kind of unpack there, and we're really back to the drawing board on this one. We're looking at increasing rates, at least with Civitas. We can't really increase the rates too much with some of these surfactants, as they do have the potential to burn. But really, this is an area that we are still continuing to work on because it does have quite a bit of upswing. So really, my summary on adulticides is this flamethrower analogy. what I'm recommending for adulticides is really one application per year. I don't promote the use of an adulticide after that. In springtime, when populations build to a peak, that's when we have your best shot, but you have one shot. You need to make it a good shot and then be okay with whatever you get. So some people get discouraged when they start seeing adults after they've made an adulticide application. I've already shown you plenty of data that didn't suggest 100% control. It is not a standalone tactic anymore either. So really do your best to make that one a very effective one, and then be okay with what you have and begin doing battle with larvicides. So it brings us to larvicides. We do have a lot more groups. I think we can feel a lot better at night when we apply these things. We have 5 classes and 5 active ingredients as far as larvicides. So a lot of classes, but the same amount of active ingredients. And we have a lot more diversity in how these products work, from really kind of straight contacts to products like the anthranilic diamides that have residual activity. This was a study that Albert Koppenhofer and I did over the last couple of years, where we looked at kind of the 4 most common larvicides. I did just notice that Albert misspelled susceptible, but we won't fault him for that. Really high densities in his New Jersey trials here. And we looked at the timing of these products at 3 of the kind of common timings. So an L2.5 would mean the average larval instar is 2.5, comes out to an average of 2.5. That would mean most of the insects are still inside the plant, versus a 3.2, which is our recommended timing, rhododendron bloom, when the insect pops out of the plant, or L4.0 would really be what we would consider a late rescue treatment. And what you can see from these general timings is that most of them work very well at our recommended 3.2 timing. So that would be your rhododendron bloom. That's when they all kind of behave very consistently. So the lower the bar, the better. And I'll put the 90% hash mark across there to show you. What we see at the early timing is Ference does a fantastic job. And I really like it in this timing. This is the L2.5. This would be like the B timing for those of you who follow the weevil track. So it has residual activity. To me, these data would suggest that the product is sticking around long enough, it's not missing anything, that it advanced to a stage where it would not be susceptible. So looks really good early, looks really good mid. What you see with all of them is that they continue to have difficulties the older the population gets. So at L4.0, you got to imagine that there's some pupae in there that are just not susceptible to any controls. So for the most part, 3 out of the 4, I think, are best timed with the rhododendron bloom. One of them, I would suggest going a little bit early based on these data that we've seen over a couple of years. So what happens if we have a resistant population? You know, it really limits what we have. Obviously, we'd like to stay away from pyrethroids, although many people continue to use those in resistant populations. Really limits our adult applications. Yellow would be more moderate control. Green is kind of our best foot forward. Spinosad and Ference are really kind of our gold standards for resistance management. And what we saw in the trials where we looked at susceptible and resistance, same graph as before on the top with susceptible. What you see as far as resistance is really Ference and Matchpoint are really our go-tos at that point. Provant is normally a really effective product, especially at that 3.2 stage. What we see is Provant and Dialogue struggle a little bit harder in controlling resistant populations. You can see that the bars are elevated from the susceptible population, but really that Ference at the early timing, or Ference and Matchpoint at that L3.2, 3.3 timing is really our best bet currently. Now, what's available for Canada? You know, again, some pretty stark differences here. Spinosad is in the older formulation, that's the conserve. And the other one would really be this new kid on the block, which is Tetrino. So Tetrino is an anthranilic diamide in the same group as chlorantraniliprole, acelepryn, or Ference. I know there's been a lot of press about it lately. I've conducted 5 trials on ABW with it. 4 that I would suggest were very strong trials. These are trials where we had good densities where we could separate differences. These are single applications. They're not an adulticide followed by a larvicide followed by another larvicide like in a program. In 2016, it was our top performer in one of our trials where we looked at split rates of split applications of half rates. So early install timing followed by a late install timing. Personally, I would caution with that just from the resistance management standpoints. Fortunately, we've looked at other things such as full rates at an early install timing, as well as full at a late install timing. In 2017, all of those plots were very clean, 100% control. And then in this year, in 2019, we looked at very, very early peak. So this would be Forsythia full bloom, the indication that the adults are just moving out of overwintering sites, compared to the adult peak, which is, again, I would suggest very early for an anthranilic diamide or an early instar. And this is a very extreme population, and we got about 50% control with those single applications at full rate. So 50% is pretty good. I think most of these treatments would suggest that they're very early for this product. What we did do very late in the year, so this was a late curative. This was the 29th of May. So we typically analyze our trial results in the first week of June. And at that time, they're mostly 5th instars and a lot of pupae. And what we see that is somewhat different with tetraniliprole is that we got very good curative control. So 62% really exceeded any of our expectations. Dialox or trichlorphon is really our curative standard, and that gave us about 16% control. And so this was not something that I expect, but based on some of the data packages that some of my colleagues have, it seems to be supported by their work as well. So it's something new that's going to be on the market for sure. So really, if we get too far along, we do have to be okay with sitting on our hands, not doing anything. When the majority of the population are pupae, such as this picture taken from some trials that we evaluated in the middle of June, where they're mostly pupae, when I get calls at this time of the year and people say, this is what I have, it's really not much we can do at this point. So waiting until the next round comes along. And it can be a significant challenge. It can be a long wait as well. We might be waiting until the first week of July or mid-July in our part of the world before we're taking action again. So that's a long time for me to tell you that we can't do anything, but any control at this point is only going to be minimally effective on the population because you have so many pupae in the environment. In 2018, 2019, we've seen a lot of 2nd and 3rd generation damage. Part of it is what we believe is due to excessive rainfall that really can move some of the products away, most likely horizontally, where we get these delusions of rainfall, ½ inch or more within 24 hours. But I do think that resistance is also a big driver of why we're seeing so many weevils being carried over into 2nd and 3rd generations. Now, what can we expect when we have wet years where we have puddling of water? I'm not really concerned about our adulticides. They bind quite tightly to the organic matter. I'm not concerned about spinosad to that much of a degree. If you remember with the old formulation of Conserve, this was suggested to be put in with about 1/4 inch of water, so almost immediately to get it out of the sunlight. It has some pretty good binding activity. Dialox, again, is kind of been downgraded on my larvicide chart, if you will, but I wouldn't expect too much of an effect on that as well. The ones that I'm most concerned about would be the anthranolytic diamides and neonics. They are very mobile products. They can be very, very effective, but we need to really be concerned about what kind of rainfall we have in the forecast right around our applications. We really want to make these things work very well, but we need to be very deliberate about our applications. All right, so just to wrap up in a couple of slides, hopefully, only because I'm running out of time, is kind of showcase some of the things that we're doing at Penn State to make our chemical control programs work that much better, and it seems to be a natural fit to put cultural controls along with that because they are pretty resilient to changes in the environment, but also there are things that we're already doing on our operations that need slight modifications. So we have been looking at where we can have the biggest impact. I'm going to just advance through this because I'm running low on time, but our biggest input, could be in area on fairways, and that's usually pretty common where we have damage. What seems to be uncommon damage is in putting surfaces, unless you're trying to control the weevil with fungicides and you're mowing at a very high height of cut. But really, this seems to be an area where most people are applying insecticides, and yet damage to putting surfaces is rather rare. And so over the last few years, we've looked at, why is this such a rare phenomenon when we do see adults being walking across the surfaces? Are they being killed by mowers? Are they being removed? Are there predators that feed on the eggs? Or can larvae not even develop in a height of cut that's that low? What we do see is that the insect does change its behavior as far as egg laying in putting surfaces. So on a fairway height of turf, the insect will chew a hole in the stem of the plant, insert the egg. But at a putting green height, what we see is that the female will just deposit it pretty much on the surface. Those eggs will hatch out and can burrow into the plant and develop just fine. So what we did see from this research is that they do still pose a threat to even greens mowed at 1/10 of an inch. However, some work that Ben Suzuki did in my lab showed that what we were expecting was that at lower mowing height, we'd be killing a lot of the insects with just the mowers going over the turf. But in fact, what we're seeing is no matter the height of cut, really there's no significant difference in the number of weevils that are killed by mowers. What is significantly different is that the lower you mow, the more you remove, and that they go through the blade, they go through the reel, and they survive, the vast, vast majority. But this may be why we don't typically see damaged putting surfaces unless we're at the higher end of the spectrum, is that so many of them are being removed. So it's really important to manage your clippings. Over the years, we've looked at things like double cutting, we've looked at rolling, we've looked at a variety of brushes as well, things like hard and soft brushes, rotary brushes that go on the roller, the turf trainer, and we've compared it to mowing heights. And so what we can summarize over our several years of working on these different areas is that double cutting is numerically, but not statistically significantly better than one-time mowing events. What we do see is that the biggest improvement, much like ball roll, is at the higher heights of cut. So just like double cutting at a higher height of cut, you're removing more of the stragglers, you're removing more of the straggler insects. So I wouldn't expect to see a big difference with double cutting unless you were mowing at 140 or higher. With brushing, it was pretty surprising. We did see about the same as what we saw in our mowing studies with 27% removal at a mowing height of 110. When we combine that with a soft bristle, both of our less aggressive bristles stood the plant up and were capable of removing 50% of the adults from infested plots, whereas the hard bristles and the turf trainer did not remove any of significance. As far as rolling, we saw a pretty minimal impact, but it is something. With 2 passes, we were getting about 10% removal. So all of these things combined are kind of small cuts that end up probably helping on the long term, especially when we think about doing these practices multiple times throughout the week. Other areas that we're working on at Penn State, as we move from a world that probably isn't going to have a whole lot of adulticide options, scouting is going to be a premium, and understanding where these insects are located can probably greatly lessen the amount of larvicides that we're putting out in the environment. Currently, we're working with a company to come up with these NDVI as well as other spectral imaging software that allows us to detect populations feeding in the turf in advance of damage so that we possibly could apply something that has some curative activity against the insect. So this year, we're scaling it up from handheld scanners into drones on the golf course. But really the future that I'm banking on anyway is in my PhD students, and they're really working on some advanced things because they're much smarter than I am. But this is Garrett Price. Garrett's been working in my laboratory for the last couple of years, and he's looking at resistance issues in the insect and the role that gut bacteria provide in conferring resistance. So pyrethroid resistance, we know, is at least in part due to increased enzymatic activity and the ability to break down toxins before they reach the target site in the insect. And we do know that insects such as weevils have numerous amount of bacterial symbionts in their gut that are capable of breaking down insecticides. And so what Garrett's done over the last couple of years is use Bethpage as his study site, because Bethpage has multiple golf courses with different intensities of insecticides where we can test these hypotheses that gut bacteria in particular detoxify these compounds. So he's taken collections from the green course, which is their low or organic input golf course, which borders the red, which we would characterize as our medium inputs, as well as the black. So they all kind of touch, and the black is being the highest chemical input. And so what he did is he collected weevils from these different courses that have been subject to different chemical intensities over the years. He extracted the DNA and sequenced it. And we also did some resistance assays. So I had characterized these golf courses back in 2014, and even in 2018 and 2019, the resistance level has pretty much stayed the same. So it's at least not reversing it. And it was nice to see that Garrett's work mirrored my earlier work. But what was really interesting is that he has identified a key bacteria that is found in the resistant population. So what he has to do now is really characterize that genera of bacterium to see if it is degrading the insecticides over time. The exciting thing from our standpoint is that the database would also suggest that this genera of bacteria is also found in Argentine stem weevil, which is a very close relative of the annual bluegrass weevil. It's a problem in New Zealand pastures as well as golf courses in New Zealand and Australia. The other thing that he's going to be doing over the course of the next year is really isolating that bacteria and then reintroducing it. So hopefully we can restore susceptibility to resistant populations down the road by knocking out these bacterium, if indeed they are conferring resistance. The other student that I have who's just started in January is Audrey Samard, and she's going to be looking at annual bluegrass weevil's relationship with creeping bentgrass. Why is creeping bentgrass a much more tolerant host? Why is it able to support greater densities of weevil? And look at the different plant defenses that are present in creeping bentgrass and annual bluegrass, and whether or not we can prime that plant to be much more tolerant. It might be a solution for reducing our thresholds, or increasing our thresholds rather, to feeding damage. So really just to conclude, as I'm a couple of minutes over here, but really, you know, best management practices for 2020 is still the same as it was 50 years ago. It's about timing, timing, timing. I would contend one adulticide, not 1 and 2, like it was suggested 50 years ago, and then be good for the year with the adulticide. But really rotating larvicides, we have some very effective larvicides as long as we haven't abused the adulticides in the past, and we want to keep those products working effectively over time. 2 well-timed applications is still the best remedy for this insect. It really coming out of the gates, being deliberate, having your timing properly, an adulticide followed by an insecticide, and then hopefully it's really just minimal spot treating throughout the rest of the year. Again, we've got to be okay with less than 100% control. I think there's a lot that we can do culturally to support higher populations of weevil without our clientele noticing it. And we really need to do those things. So really mitigating stress on the turfgrass stand, but really kind of doing everything right, being okay not to make super amount of insecticide applications throughout the year. With that, I'd like to thank a lot of people I know Scott Fish is on the line, Country Club of Harrisburg. I'd like to thank you for all your help, as well as all the other golf courses that we do research on, and especially the 11 GCSA chapters that have helped with funding of different projects throughout the year, and also my main man, Danny Klein. With that, I don't know if I can advance the slide here or not, or if anybody's still on the line.
Oh yeah, we're still here.
Who might have a question?
Not any questions yet. If anybody has any, pop them in there. There is a comment in there about a 1967 debutante party on Long Island where the party ended late or early in the morning. All the windows and doors were left open, and there were hundreds of thousands of adults swarmed all over the walls.
Interesting.
Vacuums were used to eradicate. 1967.
I have, looked at hundreds of thousands of weevils in my lifetime, and I think I've seen them only kind of flip their wings. I know all my colleagues have reported watching them fly around the lab. It's definitely possible. We believe that they fly back in to overwintering sites and starting in the middle of summer all the way into fall. But man, I would love to see one fly. I just haven't seen it.
Let's see. So Scott says, great presentation. See you soon. And while we're waiting, if anybody has any questions, our next presentation coming up in a couple of weeks is Dr. Maggie Ryder of University of California Extension. She's going to be talking about some herbicide alternatives, particularly as it relates to the growing issues with glyphosate. And all right, so a couple of things coming in here. You put Provant and others in two categories, but the label says you can use for adults or larvae. Ferrants for both also, so are those good for the second generation timing where both might be out there?
Oh, I think there's a couple of Syngenta people on this line who could probably answer that better than I have. But my understanding, and again, this would be my understanding in theory, what we see with Provon is that there would be some activity contact, but there would also be activity ingestion. So what we don't see in the springtime, as I mentioned with the egg laying, or at least the dissection studies, is it's kind of odd. You would think that they would come out of overwintering and want to eat immediately to gain energy. We don't really see that egg laying until after the fact that they've laid eggs. What we do see in the summertime is you see adults, newly formed adults, need to acquire some nutrition. And so that I would suspect that Provant and Ferrants would have some adult activity through ingestion in the first generation. So to make things more confusing, the first generation adults form from the first generation larvae, not the overwintering adults, but first, second, third, potentially generation adults would be susceptible to those.
All right, here's one that says, do you feel it is effective to treat? I feel it's effective to treat for adults after dusk. Sorry.
After dusk, I would say more temperature related based on our findings. So in the summertime, again, I would limit my adulticides to spring and then deal with my population through larvicides for the rest of the year. That being said, probably the middle of the day, at the time when the insects are going to be at their maximum density, so that's your forsythia half green, half gold timing, you're probably going to be treating during the day. That's just when the temperature would be in that time frame when they're going to be active. They're going to be moving out of the canopy. There's less between them. Again, that's largely theoretical. I would still try to target it when they are more active, moving in and out of the canopy, rather than treating them when it's cold and having them hunker down and maybe not moving for a couple of days and that product wearing off. I think we can drive that product down some degree with a little bit of irrigation, And I would recommend that anyway, with any adulticide to knock it off the leaf of the plant. But these things are going to be bound pretty tightly, so it's not like you're going to drive it very far down. So I think I answered a few questions in that one.
Yeah, you actually answered the next one too, which was about half green, half gold. So, and adults. Again, everybody, if there's no other questions, we'll go ahead and start to wrap things up. Again, thanks to our folks at BASF as well as Greg and Brandt for their continued support of our online education. We appreciate that and couldn't do it without them. And Ben, thanks, of course, for putting this together and doing it on such short notice as well. And with that, we'll give a going, gone on any other further questions. So don't see anything. Nice job and happy St. Patrick's Day.
Yes. Thanks
Unless
for
you're
joining
in
us.
unless you're in Ireland where they've canceled it. Can't make this stuff up. So anyway, thanks again, everybody. Ben, thanks a lot, and we'll see everybody next time.